Okay, in this podcast, I'm going to do a review of gases. So let's just first talk about KMT, which is the kinetic molecular theory, which describes the behavior of ideal gases. So the first thing, the kinetic energy of a gas is directly proportional, that's what that symbol means, to the temperature Kelvin. So temperature Kelvin is a measure of how much kinetic energy a gas has. So the higher the temperature, the higher the kinetic energy. If you remember, kinetic energy is 1/2 mv squared. So this is mass, this is velocity, okay? So the molecules that have a higher kinetic energy tend to move faster, okay? Let me erase what I just did over here. Okay. So one of the assumptions of the ideal behavior for KMT is that the volume of gas particles is negligible. That compared to their container, that their volume is insignificant. Okay. Volume can be considered zero. The other thing is that they have continuous random motion. They don't stop. They don't hit another particle or hit a wall and stop. They are continuously moving. In that they collide with each other and the walls. Although from a surface area standpoint, you have a lot more wall than you have other gas particles. So they hit the walls a lot. In that they have elastic collisions. So an elastic collision means whatever speed I hit that wall at is the speed I come off at. It doesn't slow down. Okay. And the last thing, and very important, is the assumption is because the gas particles are so far apart that they have no attraction for each other. And what you'll find out is that they do in fact have some attraction for each other. Okay, so this is another one of those graphs that comes up a lot on the AP exam. It's known as the Maxwell-Boltzmann distribution of velocities. Sometimes you'll see kinetic energy down here, and sometimes you'll see velocity, and we always see the number of molecules here. So what we see, let's say we have a gas, let's just focus on the red first, that is at a temperature of 200 Kelvin. Okay, what you'll see is that there's a distribution of speeds, that there are some particles that are moving very slow, and there are some particles that are moving very fast. But on average, the speed is an average, okay? And if I increase that temperature now, then my average speed is going to be higher, and I end up with a distribution that's broader. I have more particles that are at slow speed and a bigger tail. Okay, so the higher temperature, the broader my distribution. If this is low temperature, high temperature, I'm going to have a much broader distribution. Okay, so the key thing is there's a range of speeds. They're not all the same speed. Temperature increases, range of speed broaden. As temperature increases, we have a greater number of particles at that high speed. So if I wanted particles to have a certain speed, if I have this temperature, I have that many. If I have this temperature, I have this whole area under this curve. And if I have this temperature, I have a whole bunch of particles, the whole area under here. I can also use Maxwell-Boltzmann to compare the molecular speed of two different molecules. So here I have helium and neon. And I'm going to assume that I have these at the same temperature. And so here is my lower speed for neon and my faster speed for helium. And helium is moving faster, and that's because it's a smaller molecule, and the root mean squared velocity, which is a measure of how fast they're traveling, is directly proportional with 1 over the molar mass. So the higher the molar mass, the lower the velocity. So small guys move faster. And things that move faster have a broader distribution than those things that move slowly. Okay, so at any given temperature, heavier molecules have lower speeds. There are a number of mathematical relationships, some of which are on the pink sheet or the equation sheet. Don't forget that at STP, 1 mole of any gas occupies 22.4 liters. This can be used to get lots of multiple choice points. If I don't have STP conditions, I can use PivNert. So pressure times volume equals moles times R times T. Okay? And the important thing here is that I need to use an R that matches my units of pressure. Okay, and I need to make sure my volume is in liters, my temperature is in Kelvin, that this is my moles. Okay. The more complicated problems using PivNert might involve density. And if you are looking for density, what you're looking for is grams over volume, and what you should do is set the volume at 1 liter. Okay, so what you're really just looking for is grams. And if you're looking for molar mass, don't forget molar mass is grams over moles. Okay, so if you find your moles, you're probably told how much mass you have. You can find your molar mass. It's important also to understand what these relationships are between pressure, volume, temperature, and moles. Okay, so if I have pressure and volume, they are inversely proportional. As my pressure increases, my volume decreases, and vice versa. Okay, that is the only inverse relationship, pressure and volume. All other relationships, temperature Kelvin versus volume, or temperature Kelvin versus pressure, or temperature Kelvin versus moles, okay, or moles versus volume, or moles versus pressure. They all have a directly proportional relationship. Okay, so it's important also to recognize that what causes pressure of a gas in a closed container is the collisions with the walls of the container. Okay, and it makes sense, therefore, if I have more moles of gas, I'm going to have a higher pressure. I'm going to have more collisions. If I have a higher temperature, those particles have more energy, they are moving faster, so if I have twice as much of that, I'm going to increase my pressure. If I make my container smaller, I'm going to have more collisions with less space, which is what gives us this inversely proportional relationship. The smaller the container, the higher the pressure. Okay, so this is PivNert. If I am looking at changing, let's say, pressure and volume, and I want to know what effect it has on temperature, or I'm changing temperature, I want to know what effect it has on pressure, I can use the combined gas law. And this is the way I remember it is potatoes and vegetables on the table. P1V1. And if I don't have moles in the problem, I can just leave that out. If I don't have volume, I can leave that out, right? But any of the variables will set up this way. Effusion and diffusion can get asked about. The difference might be asked. Effusion is the movement of a gas through a pinhole. So effusion problems are things like I have a balloon and one gas has effused, which one's going to refuse faster. Effusion means going through that tiny little hole that might be between the rubber particles in the balloon. Diffusion is where I have not just a pinhole, but I can open a barrier and let gas molecules move freely. And when I have diffusion, I have gas particles that are going to spread out and eventually be pretty uniformly spread. The thing with the balloon and effusion is the large guys, as you can imagine, are going to effuse slower, right? And small guys are going to effuse faster. You know, because if you think about these guys hitting the wall, it takes some number of attempts before it actually will go through the hole, right? And the smaller you are, the more likely it is that you're going to make contact with that hole. Okay. So the assumptions for being an ideal gas is that you have no attraction between molecules, and that the volume of the gas is insignificant. Okay, so the more ideal you have suggests that the particles are further apart. Okay, and what are the conditions that are going to make the particles stay far apart? Is it going to be high pressure or low pressure? Well, it's going to be low pressure. It's going to make a gas behave more ideally, because if I increase the pressure, I'm pushing these guys together, okay? And high temperature is going to force these guys to move further and further apart. And if they move further apart, then they have less attraction for each other. So high temperature and low pressure, you're likely to get asked, what are the conditions that lead to more ideal behavior? And of course, as size increases, the volume is no longer considered equal to 0. And certainly a big factor here is if I increase the IMFs, I am no longer in a situation where I have no attractions. Now I do have attractions that affect. If I do have attractions here, these guys are going to be less free to just go slamming against the walls than they would be if they had no attraction at all. Dalton's law is important because it tells us that if I have, let's say, two gases occupying a certain space at a certain pressure, and I combine them into the same space, they behave as though the other gas wasn't even there. So if I have, let's say, 5 liters of hydrogen and 5 liter space of helium, and I have 0.6 moles of this and 1.5 moles of this, and these associated with pressures, if I combine those two gases into one container that is still 5 liters, all I have to do is add together their pressures, and I get their total pressure. What's important about this is it also tells us if I'm at the same volume, and I'm at the same temperature, then my ratio of pressures for any of the gases to the total pressure is also the same as the ratio of moles of some gas over the total number of moles. Because what's going to cause pressure is the number of collisions, and the more molecules of one gas that I have, the more collisions it's going to have. Okay, so I can look at partial pressure, and it's going to also be the same as my mole ratio, okay, or my mole fraction. Last thing here is some things involved with collecting gas over water. There was an FRQ on this last year, and a lot of students didn't really know what to do. If I am conducting a reaction and I am generating a gas, and I want to collect that gas to do some analysis, the typical process is to collect that gas over water. So I have a tube, and that tube, I fill up this graduated cylinder with water, and this tube is inserted, and the gas displaces the water, okay? And then I can measure the volume of this water. And I can measure the pressure of the room But what happens is I end up with some errors, because if let's say I'm collecting oxygen gas, and if I'm collecting it over water, I also have some water vapor. And remember, you know, the vapor of the water, the vapor pressure of the water is going to be temperature dependent. And the higher the temperature I have, the more gas molecules I'm going to have up here. So what I have to do is figure out how much of the pressure in this graduated cylinder comes from the oxygen gas I am collecting, and how much comes from the water in this situation. So I can look up on a table, let's say at 20 degrees C, find out what the temperature is, and it might say it's 13.2 millimeters of mercury. This is a vapor pressure of water table. And what I have to do, if I determine that, let's say that in the room I have 773.2 millimeters of mercury in the room, what I have to do is subtract from that the pressure associated with water, because I know at that temperature this is how much water pressure I'm going to have, and then the difference will be the pressure associated with just the gas that I'm collecting. Okay, so the key thing is you must subtract the vapor pressure from the water. And you're generally told in the problem at 20 degrees C, the vapor pressure of water is, you know, 16.2 millimeters of mercury. And that's going to be your hint that you got to subtract that from the total pressure. Okay, we're going to stop right there on gases.